Hello and welcome to part 2 of lecture 19, where we're going to continue to talk about optical devices. Here we're talking about the human eye, and we're going to be doing our first example. Okay, so we're told Martina has myopia. So if she has myopia, that means she is nearsighted. Let's write that down. Okay, that means she can see things that are close, but she cannot see things far away. Okay. Her far point is 200 centimeters. A normal far point is infinite. So far point is 200 centimeters. Okay. And we want to correct her vision, and we're going to do that with a lens that's going to allow her to see objects that are far away. Okay, so we just need the thin lens formula here. I want to start with the thin lens formula. Okay, so using that, we write 1 over f. We have 1 over s plus 1 over s prime. Okay, now we know our object are going to be things that are far away, where a normal eye would be able to see, focus on objects that are very far away. Okay, and so that means we want our object length, our s, to be infinity. That is simply the normal far point. And we want those objects that are far away to become virtual images located at this person, at Martina's far point. Okay, the far point that occurs for her eyes without corrections is 2 meters away, 200 centimeters away. So we need an image to be located at that point that she can clearly see and can clearly focus on, so that now objects that are infinitely far away, or anywhere between 2 meters and infinite, will come into focus. Okay, so our s prime is going to have to be negative 200. Okay, why negative 200 centimeters? In fact, I will leave it in meters. I'm going to convert over to meters. So, but why negative? Because it's a virtual image. Okay, virtual images created by lenses are always going to be negative. They're always on the side of the lens that has the sign convention of negative, which is the same side as the object. Right? You visualize that? How the object is infinitely far away and the image is 2 meters away, but they're both on the same side of the lens. They're both on the opposite side of the eyeglasses or contact lenses as the human eye, right? They're on the same side. Thus, s prime must be negative. Okay? So then we'd solve for f. And it's just going to be 1 over infinity plus 1 over negative 2 meters to the negative 1 power. And that's going to give us a negative value, clearly, of negative 1/2. All right? And, well, that would be 1 over f. Excuse me. So it should be, if we take, I'm going to go ahead and calculate it. Seems like it should just be negative 2. Let's see. Of course, it is negative 2. So it's negative 2 meters. Okay, so that's our focal length. Okay, that seems obvious in retrospect because our s is negative, and so essentially we're saying 1 over f equals 1 over s prime. So f must be the same as s prime. But then how do we convert that to diopters? Well, we just take its reciprocal. Okay, so right over here. And P is 1 over f. So it would be negative 0.5 diopters, which we represent by the letter D. It's the unit diopter, which is just inverse meter. Okay, so there it is. That's the lens that Martina needs to see everything from a natural near point to a natural far point, from 25 centimeters to infinitely far away. Okay? And here's the thing, right? There's a concept question down below, question 2, and it says, come back to question 1, I'll mention in a minute. But question 2 says, well, looking at a lens like this, a diverging lens, what type of vision is that used for? Well, the example we just did tells you, okay? But I'll let you be sure of that on your own. So make sure you understand what type of lens this diverging lens, what type of vision this diverging lens is used for in order to correct that vision, okay? All right. All right, I'll leave question 1 for you as well, which is if the near point of your eye is at 75 centimeters, you have what type of vision? Okay, make sure you can answer that. All right, example 2 is also left for further practice. So let's now move on from the eye to our next optical device, being the microscope. Okay, so let's find a microscope problem. And I wanted us to take a look at. Okay, so which one do we have here? 20x, yeah. So a biological microscope with a standard length of 160 millimeters has an objective lens labeled 20x. What is its focal length? Okay, so we're looking for the focal length of the objective. Okay, 20x means 20 times magnification. All right, and that standard length, I bring that up because I don't think we don't have problems in our study guide that are like this, but it's common in these microscope problems to make an assumption because there's a kind of an industry standard with microscopes. They tend to always all be the same length, but just a word of warning. Okay, so we have a biological microscope, 20x. Okay, so first we'll write what the 20x means. So 20x means 20 times magnification. So that would be MO for objective, and it would have to equal 20. All right. And let's think about this, right? What's magnification is a formula of negative H over, so H image over, we'll say, so H prime over H, so negative, using the same notation we've been using throughout these sections and these lecture notes. And then if it's 20 times bigger and it's a real image, not a virtual image, a real image, then we're going to have negative 20 because H prime is 20 times bigger and but it's a real image, an inverted image. So it would be negative 20. Okay, well, let me flip to that real fast to show you, right? As a reminder, a microscope works by creating a real image from the objective, and then that image becomes the object for the eyepiece, okay? And then that eyepiece creates an image, a virtual image, at some point, and that virtual image can be seen by the human eye, okay? Because only virtual images are we able to see. Right? Always a good reminder of that, I suppose. Okay, let's go back to the problem. Okay, so we need to find the focal length. Well, we're going to write the formula for the focal length for a microscope, okay? So this is just right out of the key formulas for this section. So F of the objective, so O for objective, is defined as negative L over the magnification of the objective, okay? And again, that's an approximation, and that's approximation because we're taking the distance between the lenses as an approximate point where the image is being created, okay? The image from the objective, that is. So here we're plugging in on negative 160 nanometers, and our magnification, okay, which is negative as well, okay? So now we have a negative and negative. It's important because that gives us our focal length, and that's going to be positive, which it should be because it's a converging lens. So if you got a negative, that's wrong. And it will be 8 times 10 to the negative 3 meters. Oh, and I realized I wrote the wrong thing just a minute ago. For some reason I wrote nanometers, even though I said millimeters. Right. 2 years writing nanometers for wavelengths of visible light. There we have it. Okay. So that is our focal length for this microscope. All right. So let's see if we want to do one more example. I think that'll be a good idea. All right. So I'll still leave one example 5 for your practice. Another microscope, right? Quite similar to the one we just did. But I'm going to do one more, and then I'm going to do a telescope example, and we'll wrap up these notes. So a student uses a microscope. Again, standard length, 160 millimeters, 16 centimeters, in other words, to view an amoeba. If the objective has a focal length of 1 centimeter, the eyepiece has a focal length of 2.5 centimeters, and the amoeba is 1.1 centimeter from the objective. What is the microscope's magnification? Right? How much are we getting? That's kind of a good thing to think about. Where do they get a total magnification number from? All right. So we know the total magnification of the microscope, and make sure I'm using the notation here. So we'll do it. Copy that over. Okay, so let's get this in our problem for reference. All right. So we're going to use this formula. We'll use the M of the micro, so the total magnification of the micro, as M1 ME, okay, which in other words is M objective times ME. Okay, so those are just the two lenses, the first lens, but I call it the M with the subscript of O in the previous example, so to be consistent, that's what I'll use here. Okay, and then we just want to think about where each of those terms come from. Okay, so, or what more like what they look like when we expand them out. So then the M for the objective is L over F, as we previously stated. And then the eyepiece is based on the human near point, so it needs to be 25 centimeters over the focal length of the eyepiece. This one's the objective. All right. So we should just be able to plug everything in now. Okay. And so let's do that. Okay, so we have our 160, okay, millimeters. And then our focal length for the eyepiece is 1 centimeter. Okay. Yeah. Looks good. All right, so 1 centimeter. So I'm kind of leaving off the scientific notation, but it would not be 1 times 10 to the negative 2, and obviously the numerator would be 160 times 10 to the negative 3. Okay. Looks good. Let's do the next part. So 25 centimeters again. I'll go take advantage and cancel that unit out. And then the focal length of the objective, the eyepiece, was 2.5. Okay. Yeah, there we go. Okay, so when we plug this all in, we should have, okay, so let's see what we get. So I'll take 160 times 10 to the negative 3, and then I'll divide by 1 times 10 to the negative 2. Okay. All right, and then I've got 25 over 2.5, because I don't have to worry about the units there, because those centimeters would directly cancel out. So 25 divided by 2.5. All right. So that gives me 160. Okay. Magnification is S over, let's see. Oh, I see. I think I see what I did here. Well, we did plug in the correct things. We're given both the focal length of the objective lens, 1 centimeter, and of the, I see, okay. So I think I see the issue here, and it has to do with how far the amoeba is. Let's see, because we're told the amoeba is 1.1 centimeter from the objective. So we can take this one's fine. This expression is fine for the magnification of the eyepiece. Okay, so we're okay there. But I'm going to have to make a correction here, which I'll do my best to explain. Okay, so the objective magnification is going to be the image distance over the object distance. Okay, and we know the object is at 1.1 centimeters, and we know that the image is going to so is the distance of the image from the objective lens. Okay. And we're definitely going to assume our standard 160. Okay, so then if I had 160 over focal length of 1, all right, so that should give us about 150. Let me check my numbers here. I feel like something is, okay, so I have, yeah, okay. No, actually this is fine. So false alarm. It just, I had a previous note here, but I see that there was just an order of magnitude mistake. Because if we're thinking about the 160, this right here is just 16 centimeters. And so then the magnification of the objective is 16. The magnification, because that's what this represents, the magnification of the eyepiece on the other hand would be 10. So we have a 16 and a 10, and we put them together, and we do end up with 160 as our total magnification. Okay, and it's negative. Yep, and the reason it's negative value is because the final image is indeed inverted, so the final total magnification should also give us a negative. Okay. So let's put that in. So negative 160. It's a total magnification. So it really was a pretty straightforward plug and chug problem. I just wanted to make sure that there wasn't some extra step to it. And then I'll also make a note here that negative because inverted. Okay, but dude, that might make you think it's a real image, but we know it's not a real image. It's actually a virtual image because it's a virtual image of a real image, which is a way you can get a inverted virtual image, but you can't do it in one step. Okay. So in this case, it's a virtual. All right, so that's our second example. The second example I wanted to show you of a microscope. So let's wrap this up with showing you a telescope example. All right. So the telescope example I want to show you is, let's see, is it this one? Microscope. Let's see. Yeah, so I'll leave, there's a couple telescope examples here. I'm going to leave these because the one that I'm ready to show you right now is example 8. Okay, but I guess you have a lot to choose from here. But let's see. Okay. So example 8, the eyepiece of a refracting telescope has a focal length of 9 centimeters. Let's see. Excuse me, example 9. I think I'll probably go back and do another one, but let's take a look at example 9. So the objective lens and eyepiece lens of a telescope are 1 meter apart, and the telescope has an angular magnification of 50. Find the focal length of the eyepiece and of the objective. Okay? So what we use for this is one of our telescope equations. So take a look at here. We really just, I guess, have the one. All right, so I'll take a screenshot of this. Okay. So what do we know? Okay, so we're told that the distance between them is 1 meter. All right, and then 1 meter will be the approximate length of the focal length of the objective. So L being 1 meter is a roundabout way of telling us that the focal length of the objective is 1 meter. Okay? And that's because the approximate location of the image formed by the objective is at the eyepiece. So the image is approximately formed immediately at the eyepiece, like right on top of the eyepiece. All right, and that's just kind of to get, it's an approximation, but it's a good way of thinking about telescopes, and that's getting an effect that having it so close is going to create a very, very large magnification, or it's going to create, even more so, it's going to create an image that is infinitely far away and that you can see with a relaxed eye while looking through the eyepiece. Okay, but that is just something that is, in the material of how we approximate telescopes. And obviously there's lots of levels of discussing these optics, but this is the basic level to talk about it. Okay, so then we've then got the eyepiece. Okay, so we know the total. Okay, yeah, so then it's just a matter of, saying then if you have a total magnification of 50, well, you can probably see then, right? So then M tel equals 50 in this case, which by definition is just objective focal length over eyepiece focal length. Well, then we just solve for the eyepiece focal length, which would just be the objective over 50. All right, well, we found out that we already know what the focal length of the objective is. It's just 1 meter. So then we'll just have 1 meter divided by 50, which gives us 2 centimeters. Okay, so that is the focal length of our eyepiece. All right. Okay, let's see. Yeah, we'll go ahead. I'll leave the rest. I want to wrap up this video, but I at least wanted to show you a couple more examples from calculating a pair of glasses for the human eye, to looking at a couple of microscopes, and then one telescope example. All right. Obviously, a lot of them are left done, and I definitely will circle back around and write in some solutions. But I would recommend you take a look at these or those in the study guide. Make sure that you get some practice with how to use these formulas, because they're not difficult, but it really is best if you read that chapter and make sure that you understand the rules that we're following here. Because more than deriving things from like first principles of physics, this is just about remembering a couple of important rules. All right, well, thank you for watching.